Okay, so last class we ended with a little history of motors. So we saw the first electromagnetic motor was invented by Michael Faraday, a British guy, back in 1820. And that was not the first motor. The first motor we saw was invented by the Scottish monk. And that was back in 1740, and then it got renamed as Franklin bells, while it should have been Andrew Gordon bells, right? So all the motors that we see on our table here, do you think they are electrostatic motor or electromagnetic motor?
Electromagnetic.
Electromagnetic. Do you know why? Have you seen any electrostatic motors in your life? Anybody seen an electrostatic motor in their life? Anybody want to give a reason as to why electrostatic motors are not common? Okay. Those of you who took the electromagnetic theory course, what is the energy stored in an electric field? Equation for an energy stored in an electric field? Anybody remembers? So the energy density of an electric field is given by epsilon naught E squared. And then we look at the energy density of magnetic field as well, and which we will derive later when we go over the fundamentals of electromagnetic theory. I usually try and avoid giving any formulas unless it's a definition or a fundamental law of nature. Otherwise, we'll derive each and every single equation. We won't take anything for granted in this class. Right? But just for this lecture, bear with me as I throw a couple of equations, but we will try and derive them later in class. Okay, so this is our energy density of an electric field. And the way these motors work is there is a stationary part, and then there is a rotational part, and energy is transferred from the stationary part to the rotational part by some kind of air gap that separates them, right? And that separation is required because the mechanical isolation is needed so that one can rotate, one can remain stationary. And the term rotor and stator is somewhat rather arbitrary. If I hold on to the rotor and turn on this power supply, the stator is going to start rotating, right? Stator is just something that's supposed to be stationary, but if you operate it wrongly, even the stator can rotate. There is nothing special about stator or rotor. Whatever force the rotor is experiencing, the stator is experiencing the same force. It is just that it's mounted onto the table or some kind of frame that it's not rotating, just the rotor ends up rotating. But there's nothing special about stator and rotor. But at the end of the day, there's basically an energy transfer from something that's stationary to something that's rotating through an air gap medium. And the same thing happens even in an electrostatic motor. There would have to be some air gap medium that separates the stator and the rotor, and then energy transfers to that medium. If this electric field is too large, the medium itself will start to puncture. That's what we saw in Andrew Gordon's motor, right? Where we had this tower-like arrangement and we had this pinwheel structure. And what this was doing is basically puncturing the air medium and then using the ions that were generated to push this forward. But this is not particularly a good way to operate a day-to-day motor, because one of the problems is whenever this breaks down, this oxygen is then going to go and react with the metal here and form, if it's copper, it's going to form copper oxide, which becomes non-conductive. It is not a sustainable way of having a motor which keeps breaking down after a couple of days, right? Because it's constantly getting deteriorated. The metal is being chipped away bit by bit every time that oxidation happens. So whatever electrostatic motor we create would have to operate below the threshold where the air starts to puncture. All right, what was the electric field at which air starts to puncture and we get corona discharge? Anybody remember the value? Yep.
You say 3 kilovolts per millimeter?
3 kilovolts per millimeter, okay. So E max for air that we saw was 3 million volts per meter, or commonly just 3 kV per millimeter. Right, so above this, if we try to put, so we have 2 parallel plates of some mechanism, and then we put an voltage large enough such that if you divide the voltage by the separation of this plane, and all that is separating these two is pure air, nothing else, then we would end up having corona discharge that happens. So we want to avoid it, but push it up to that point. So let's try and see at this maximum value that's possible, what will be the energy density that can pass through this medium. All right, at any other voltage, if you want to pass any more energy through this medium, then you would have to go to a higher electric field, which would then collapse the medium itself. It no longer functions the way we want it to function. So for that value, the energy density comes out to 1 by 2. Anybody remember the value of epsilon naught? Permittivity of free space? A rough number is also okay? Yep.
3.85 times 10 minus 12.
Perfect. 0.54. By the way, don't feel bad if you don't remember. I had to look it up before class. I keep forgetting it every time. I just remember it as 9 into 10 to the power minus 12. And then E for E max is going to be 3 into 10 to the power 6, the whole square, right? So this 10 to the power 6 whole square becomes 10 to the power 12, 3 square becomes 9. So we have 9, 9, 10 power minus 12, 10 power 12 gets cancelled. So we have 81 by 2, which is roughly 40 joules per meter cube. So this is the energy density. So if you create some kind of planar capacitor such that the volume within the capacitor is about a meter cube, the maximum energy that can be transferred through the air gap medium is about 40 joules, above which the medium itself will start to puncture and collapse. So this is the maximum we can do with an electrostatic motor. We definitely do not want to exceed this for a day in out operating motor. And as we'll see in just a minute, this energy is rather extremely trivial. Not at all comparable to the motors that I have on the tables or even the motor that's a simple motor that's in your watch. Right? So there are two ways we can increase this energy density. One is either going to a higher electric field, but that would require changing the medium because air cannot sustain a larger electric field. How many of you have taken power systems course? All right. So what kind of material is used in the relays when they open the switch gear? There's a special fluid that fills the switch gear so that the discharge does not happen. Typically, when you open a high voltage switch gear, you would see that arcing, and that again is detrimental, and you want to avoid it as much as possible. So the one way they do it is have a closed, enclosed switch gear that's filled with SF6, sulfur hexafluoride. It's an extremely potent greenhouse gas. I think it's almost 20,000 times more potent than carbon dioxide, and it lives for a very long time in the upper atmosphere, doesn't decay down quite easily. So it's a very big problem. It's still used in switchgear because one of the best materials that's available, but it's a very potent greenhouse gas that people are trying to phase out, but no better material has come out. So SF6 switchgears typically can take voltage up to 9 million volt per meter. All right, not that much. You don't get too much by changing the medium from air to SF6, and you get all this disadvantage by going to a different medium like SF6. There are other liquids which have much higher electric field capacity, as well as if you can modify this factor. So if you use a medium other than air, the formula would end up being epsilon r relative permittivity times E squared. So if you can make this epsilon r really large, you can still get away with a different medium. But the problem is that higher epsilon r typically occurs only for things that are solid, which would then defeat the purpose, because with solid, there is no rotational isolation between the stator and the rotor, right? Or the liquids also sometimes have this property where you can get epsilon r up to like 20,000 or 30,000. But the problem is putting a liquid in a rotating medium is what's the problem?
Friction.
Friction, perfect. So you're going to get a lot of viscous friction. The minute you put instead of air gap, you have some other fluid. As the rotor rub past this fluid, it's going to have a lot of friction. So your motor is not going to be as efficient as you want it to be. So typically electrostatic motors are used only in MEMS, microelectronics. And there's a lot of research going on where when you have like tiny robotics and that we want to put into our blood within our veins and they have to navigate and go somewhere, you typically can't put a DC motor in there, right? You can't take your own energy source, your own commutator, your own control, all of those and navigate. But electrostatic motors typically can be made extremely tiny and they can produce sufficiently enough torque that they can operate on whatever they are trying to do. And it's still in an early research stage. But there is one person in Wisconsin, Madison, who's working on making electrostatic motors work even at much higher power. But it's very limited application, though we cannot use it for cases where the rotational speed has to be large. Because rotational speed becomes very large, friction becomes exponentially larger, right? And once friction becomes large, the motor is as useless as not having anything. So it's still, again, both of these are at research stage. The higher power electrostatic motor from Wisconsin, Madison, they already have a company and they're trying to commercialize it and stuff, but still pretty early on to say if it will be a success or not. So let's see why then people use electromagnetic motors instead of electrostatic motor. Let's see what the energy density of that comes out to. Anybody want to tell me what the formula for energy density of a magnetic field would be? take a guess. Magnetic field and electric field are closely interrelated. In fact, if you move at the same speed as the charge that's causing the magnetic field from that referential frame of where you're moving at the constant speed, magnetic field will appear as if it's an electric field. Right? That was one of the fundamental discoveries of relativity. But yeah.
So you just take the same formula, basically.
All right. Is that the only thing I need to replace?
Epsilon naught was mu naught.
Perfect. And it ends up going on the denominator. Again, we'll derive this in our class later, but that's what the formula comes out to. And if you look at these motors that we have here, in case of air, we have this limitation in the electric field where in case of air, we have the limitation in the electric field where if you go above it, the medium is going to start to puncture. In case of motor, we have a similar limitation, but it's not that the material is going to puncture, the material is rather going to saturate. Again, we look at the theory of how it will saturate everything, but for now, just think of it like this. You can start putting, take an iron bar, wind it with some coil, right? A closed iron bar, a toroid of some sort. And you start pushing in more and more current, and you have some kind of sensor, Hall effect sensor or something, with which you measure the magnetic field that's being generated. Initially, it will appear as if it is linearly increasing, right? After some point, it will start to saturate, right? And then once it saturates, it no longer makes sense to keep putting more and more current because you can double your current, but you won't see double the increase in the B field. It becomes almost less and less rewarding to put more current because putting higher currents is also a problem. First thing is how do you generate the larger current? And the second thing, higher the current, higher the losses because you have I square R losses in the windings that are creating the magnetic field. Right? So there is optimally you would operate it such that it's just in the region of saturation, but not well deep into saturation. So typically when you have an iron core, silicon steel in particular made for machines, you wouldn't try to operate it more than 1.5 to 2 Tesla at the best case, right? So let's take the lower limit just to give a fair competition to whatever energy density the electric field came out to. So let's use the lower limit and let's start with 1.5 Tesla. So that's the maximum B field. Let's say we are ever going to be able to operate our motor in, above which it doesn't make much sense. It's not rewarding enough. So let's substitute the values. So 1.5, that's just 3 by 2 times the whole square. Anybody know the value of mu naught? Permeability of free space? It's a very nice number. Who gave the answer for permittivity? 5.7. Go to the 5, get to the power plus 7 or minus 7? Minus 7. The most critical piece of information because we saw that epsilon r, which was on the numerator, reduced the energy density a lot, while this 10 to the power of minus 7 on the denominator increases the density significantly. And the number, if anybody wants to work out the math real quickly, or otherwise I worked it out before I came here, I think this comes out to about 900,000 joules per meter cube. So that's roughly, if I'm not wrong, 22,000 times. So it's 22,000 times what air is the operating fluid in both cases. Right? Even in this case, the separation between the rotor and the stator is just air. There is no special material or anything. Right? So in both cases, air is the operating fluid through which the energy from the stator goes to the rotor. In case of the magnetic field, you can pass 22,000 times more energy compared to what you can pass through an electric field. And that's the reason all the motors that you see on the table, every motor that we discussed last class, around hundreds of motors, all of them use electromagnetic principle rather electrostatic principle. So in this class going forward, we are not going to worry ourselves with electrostatic motor at all. We are going to completely forget this ever existed. And we're only going to concentrate on electromagnetic motor. Okay. Any questions so far? Okay. So last week we started looking at the history of motors, and the first motor, electric motor, was created by Andrew Gordon, which was the electrostatic motor that we just analyzed, a Scottish monk. And he also invented what is called as the Franklin Bell, eponymous to Benjamin Franklin, who imported this idea basically from Andrew Gordon, likely when he was in England, posted back in around 1950s. Right? So, and then he made it popular in the US and the name stuck with him. So it took another 80 years before the first electromagnetic motor came into picture. And it was during this time period, early 1810s to late 1820s, when three key contributors, Ørsted, Danish, and then we have Ampere, French, and Michael Faraday, British. So all those work culminated with Michael Faraday creating that apparatus of the early, what we can consider as a DC motor with a liquid commutator, mercury, and then there's a chalice with a magnet in between the stem. And when we have a copper rod, pass some voltage across it, it's going to pass some current through it. It's going to start rotating because the force experienced by a current carrying conductor in the magnetic field. As we saw the equation last week on Wednesday, the Lorentz force equation. Right, so that was the first DC motor, if we can call it that. Right, so that was the earliest mechanism demonstrating that a current carrying conductor rotates in a magnetic field, experiences a force in a magnetic field. So the first motor without this liquid commutator that was created again was a DC motor in 1834 by a guy called William Sturgeon. Anybody want to guess which country? Right, British. And this wasn't a practical motor. It didn't have any sort of commutator or any such mechanism. So it's just a kind of a demonstrative prototype that didn't get picked up or get used. So in 1835, Thomas Davenport creates the first commercially used motor, again a DC motor. He's from Vermont. It used these commutators for the first time, but not the commutator that we know of with these copper segmented and the graphite brushes, not the ones that are there in the motors that we have on the table right here. So this motor suffered with a very big problem. Every time the coil commuted, or basically half a rotation, there used to be a huge arc that goes across because the current path used to be broken. And that didn't make it very useful because it wasn't an efficient system. And it got used in a couple of printing presses locally, but otherwise it didn't go too far, particularly because the commutator wasn't the commutator that we know of. It's not perfect. And also the other bigger problem is electricity was not widespread just as yet. It takes another 50 years before Edison starts to electrify most of New York, right? And DC power starts to establish and then later gets replaced by AC power. It's still another 50 years before that starts to happen. So these were all some kind of battery operated mechanisms. So it was not particularly useful. So not becoming too commercially viable. And it takes another 50 years, a long winded pathway, before we get to 1884, 85-ish with Frank Sprague. Who creates the first commercially viable DC motor, and it becomes an instant success because it gets started used in railways, which were being powered by DC energy system that Edison was a big proponent of. So it's somewhat of an interesting story behind Frank Sprague. He actually worked for Edison, right? And of course, he is American. So he worked for Edison, and he had a little bit of a falling out with Edison because Frank Sprague believed that DC motors would end up being the biggest load for power system. But and he is proven correct because industrial loads are mostly motors, particularly induction motor, and motors are majority of the load on a typical power system grid. On the other hand, Edison believed that lighting would remain the most prominent load throughout. But now we know that lighting just accounts for 10 to 15% of a typical electrical load on a grid, right? So because of the falling out, he leaves the Edison electric company, and he forms his own electric, I think the name is Electric Railway and Motor Company. Do check it. I might have swapped the name motor and electric. So due to the electrification of New York and other areas by Edison, he kind of he makes a huge success out of the motors that he had designed and made available. So this is where the story for DC motor typically comes to an end. Afterwards, of course, there are a lot of people who contributed to make it better, different design structures and all of those. But this is pretty much the place where most of the changes happened from the initial version that Faraday did to the version that Frank Sprague started selling around New York. So from here on out, we're going to look at AC motors, how they come about. So one of the biggest problem with the DC motor is this commutator that we have. It is, even though the one that the Frank Sprague created does not arc as much as what the mechanism Davenport had, it still is a very lossy equipment and it occupies a lot of space and the brushes wear out over some time. So they have a huge maintenance requirement and so on and so forth. So people were already trying to see and figure out if the commutator can be eliminated. So in 1884, 85, again, time period, there is this Hungarian, Otto Blatty. He creates what's basically essentially a power measurement device. So it's a coil which carries current. So let's say you have an energy meter in your home. Before coming from the utility, there is a current carrying coil, and then the output of it comes to your home, the wire. And in addition, the voltage is also measured. So across this coil, the grid voltage is directly connected, whatever is coming to from your utility. And between these two coils, these are maintained at 90-degree separation physically. And then there is a rotating disc, a disc that can rotate, some kind of copper disc or some electrically conductive disc. So when the current passes through this coil, there is something called flux that's created. And same way, when there is a voltage applied across this coil, there is a flux induced, varying voltage applied on this coil, there is a flux induced in the coil. And these two interacting fluxes create something called eddy current on this disc, which in turn experiences forces from this flux and they start to rotate. So that's basically the overall idea. And the energy meters that you typically have in your house nowadays does not operate on this principle. So they would typically be a digital energy meter. But I used to live in this very old apartment that was constructed back in 1912. It's still there on Hennepin Avenue and I think 33rd. And in the basement, they have these still old energy watt meters that have these discs still running. So, but yeah, this was the earliest idea for measuring power and energy, but it does basically work it's on some principle like an AC motor of sort. But next time, every time you get a very large electricity bill during winter, you know exactly whom to blame. But so in following him, in 1885, later part of 84 and 1885, there is this Italian physicist, Galileo Ferraris. So he creates the first induction motor, and he was an academician. He did not patent this idea. He did not publish this idea. So he did it as a demonstration for his class, and that was about it. But what he had essentially done is created a two-phase induction motor. Right? And then in 1888, Nikola Tesla modern day Croatia. Back then it was part of the Austrian Hungarian Empire. So he gives a seminal talk in the organization that later becomes IEEE on how to design an induction motor and a permanent magnet synchronous motor. And both of these were two-phase system. And they are they do not have too much similarity except for their fundamental operational principle. They are extremely different from the motors that we have on the table right here. So the motors that we have on the table, they have they are a three-phase system, three-phase motor, and their rotor structure is also drastically different from what Nikola Tesla had designed. So Nikola Tesla himself had sold this to Westinghouse, patent for this, on July 7th, 1888 for $74,000. And for every HP of motor that was manufactured, he gets a royalty kickback of $2.5. This didn't pan out too well. This is about $2.4 million in today's amount. Right? And he went on to use this to create other ventures and so on and so forth. But this itself was not a viable product again because Nikola Tesla was very adamant that two-phase system is the way to go. But as you will see, two-phase system is not advantageous compared to a three-phase system. So three-phase system became the way. And in 1888-89, Russian engineer, Russian-born engineer, Mikhail Dobrovolsky, creates the induction motor that we know of, the three-phase induction motor, and he creates both the rotor structure that are common. The most common is squirrel cage, and he also creates the model for the wound rotor. Wound rotor induction motor, right? Which are used intermittently here and there for wind turbines, especially at higher powers. Right, and the squirrel cage, because that's the motor that we have on the table right here, a squirrel cage induction motor. And it's called as such because the rotor looks like a squirrel cage. It does not have a magnet. And I don't know which monster creates cages for squirrel, but apparently that's what it looks like. And I haven't seen a squirrel cage, so don't ask me if that's true. The advantage of these induction motors is that they do not use a permanent magnet or any sort of magnet at all on the rotor structure. There is just a bunch of copper rods shorted together, and that somewhat magically interacts with the stator created flux and starts to rotate, right? So the reason we looked at all of this theory is not just because it's exciting and I love theory, history. It is because to give a perspective, when I myself learned motors, machines in my undergrad, we used to always start out with theory of DC motor, get into all the equations, and then go to the theory of AC motor. And it'll always look as if it was an extremely fascinating jump. How do people come up with these ideas, right? And it's somewhat not unnatural to feel dejected as if only great people can come up with these amazing ideas. It's almost too big a leap to even dream of. But when you go back and look at the history and see the development, it's always incremental, right? As brilliant as these people were, as intellectual giants they were, it is not out of reach for any one of you in this room to create the next motor that could revolutionize the world. Right? Because the change is always incremental. History always will remember the kings and the queens and the eras and the periods, but it ends up forgetting the foot soldiers. So a whole bunch of people have been forgotten, but they all contributed to what ends up being pinnacle of our evolutionary history. Right? So it's always inspirational to keep in mind all the contributions other people have done so that we ourselves know that we could be the next one added on to this long list of people who have done great things. So before this, there is one critical piece of information in this intermediate time period. In 1824, there is this French physicist, Francois Arago. He creates this contraption that demonstrates a rotating field. So what basically he did is he had this horseshoe magnet. For those of you who do not know what a horseshoe magnet is, we'll look at it in, we will see an image of it later in the lecture, later in the class. But basically a U-shaped magnet with the poles right next to one another. There's reason for doing that, especially with like alnico material that were common back in the day. And he put a disc in between this system, and then he had a needle which can indicate the direction in which the magnetic field is being created. And when he spun this disc, he noticed that the needle starts to rotate along with the disc, indicating that there is some kind of magnetic field that's created that's actually rotating in the air gap. And this is very critical because that is exactly what an AC motor is doing. The stator winding is creating a magnetic field that rotates in the air gap. And along with it, the rotating magnetic field ends up pulling the magnet that's on the rotor as it keeps rotating. In case of permanent magnet synchronous motor, in case of induction motor, it's a little bit more complicated theory we'll get into. All right, so this was a very important theory that demonstrated that AC motors are feasible. So when these people started working on AC motors, it wasn't like they were completely blind, that they just happened to discover upon this phenomena where the AC motor suddenly rotates without any commutator mechanism. There was a theory, there was a demonstration that was already showing that rotating fields are possible, right? And the people who came later exploited that principle to get away from the problem faced by DC motor, which is the requirement for these commutators, which are extremely problematic, right? So with that, let's look at a couple of demonstrations for today. Oh, before I forget, there was something very critical that happened during this time period. Does anybody remember what happened during this time period? And there are multiple important things that happened that enlightened our civilization to a great extent in multiple fields. Anybody want to take a guess? All right, Civil War. Between 61 to 65 of emancipation. Right, and then during the same time period, 61 to 65, Maxwell publishes two papers that condenses all of the works that were done by the people prior to him, right? Basically the 5 equations that we know of today. So the form that he had is not the simple 5 equations that we know of today. There were a bunch of 22 equations in terms of force and a whole bunch of complicated mathematical notations that he had created. But the form that we know of in terms of curl and divergence is the nice delta symbol, inverted delta symbol that you see in your electromagnetic theory class. Those were actually thanks to a guy called Heaviside, a brilliant mathematician. You would have heard his name multiple times in various math courses. But one of his contributions was cleaning up the Maxwell equation to the simplified form that we know of today. In the additional reading material on Canvas, I have posted the original Maxwell's equation, the way he wrote it, the original paper. It's, I think, a 60-page paper. Take a look at it. It's a very interesting read. I wouldn't be too surprised if none of you understand what is going on, because it's a very hard read. All the notations that are there are completely different from the notations that we are used to nowadays, right? All the symbols for the force, all the symbols for the differential, everything is different from the math notations we use today. So it's a little bit tricky getting into it without knowing the mathematical history of different symbols that are used in different time periods. But it's always a fascinating read to just see his thinking, at least the text that goes along with the equations are very interesting to see what his thought process was. Right? So Maxwell's equation itself helped us provide a lot of enlightenment That later led us to realize that light itself is an electromagnetic wave, which this was a question of what light is. It took about 3,000 years of different philosophers thinking about it, arguing about, debating about it, without having any idea what light was. And here comes a theory that then later explains what light is. And this is the same theory, the discrepancies that are observed in this theory, where if you are looking at a magnetic field and there is a charge moving near the magnetic field, it experiences force. But what happens if you move at the same speed as the charge? It shouldn't be experiencing force, right? But it still experiences a force because magnetic field behaves like electric field. There's a whole bunch of discrepancies that occurs because of these Maxwell's equation. And figuring out those discrepancies, what led to the theory of relativity and so on and so forth, the next set of revolutionary idea that comes later in the 20th century, right? And during Civil War, both sides of the people, on both sides, both the people who were for emancipation and both the other side who were for subjugating people, used Bible as a way to argue their own position. The people for emancipation used to argue that we are all created equal under the image of God. We are all God's children, and henceforth we should not be treated differently. And the people who are arguing for subjugation say they refer to the same book and say that even in the Bible there are texts that says how to handle a slave, how to treat them, and so on and so forth. So Bible does condone that kind of behavior. So both sides were arguing about it. But just before this, 2 years prior to the beginning of the Civil War, comes this revolutionary idea, theory of evolution, by Darwin, Charles Darwin, who comes about and say, hey, you know what, we all come from, irrespective of what species you are, we all come from the same evolutionary tree. It was a remarkable idea after decades of studying fossil records and different species, not fossil record, different species and how they share similarities. He comes to this conclusion. It was very controversial during his time period, but now most of us accept that that's the reality. Most of us in the scientific community accept that that is, of course, the reality because there's overwhelming evidence that it can somewhat impossible to disprove it at this point. And it is not until 1870 where he links humans to the great apes. Right? The timeline wasn't known during Darwin's period, but now we know that we have evolved from the great apes and ourselves, diverged from the same ancestor around 3.4 million to about 5 to 6 million years back. Right? So we came from the same background. So all of us, irrespective of our race, our color, what religion we practice, we are all exactly the same. Right? So with that, let's look into doing some demonstrations for today. So on the table here, I have a couple of setups. On the left, I have a DC motor and a DC motor and a generator coupled. And then this black box right here is a power electronic converter. I'll get to it, what it does in a minute. And then we have a power supply which is powering all of this. Here, on the right is the induction motor. On the left again is a DC generator. Again, there's no difference between a motor and a generator. It's just that if it takes power out and converts it mechanical and converts it to electrical, we call it generator. The other way around, we call it motor. And then the one on the center here is on the, it should have been, so all the generators, I'm going to put it on the right, and all the motors, we are going to put it on the left. And then we have a permanent magnet synchronous motor on the left, my left, and then the DC generator coupled to it again on the right. So the setup that we have here, what we're basically trying to do so the setup that I have there, I have a power supply, which is giving me an output of 40 volts. And the current can be it can give up to 5 ampere current. And then I have a power electronic converter, the black box. Okay. For now, it's going to remain a black box for us. In week 3, we'll figure out what's exactly going on inside. But all we need to worry about is, given a DC voltage of 40, it can convert and create an output going anywhere from -40 to +40. Right? So, and there are multiple outputs coming out of this converter. I'm going to use 2 of them to connect it to the motor. in case of DC. And if it's an AC motor, I would use one more line, right? So let me draw that and dot it if it was AC. So in AC, it will be three-phase, in DC, it will be two-phase. Just two wires, not two-phase, right? And then we have a generator, which is always, we are going to be using a DC generator. And these two are mechanically coupled to one another. Right? So what basically happens is, let's say I want to create this, and you will be doing this in the lab. Let's say I want to create a drive for an elevator. So we have an elevator system. There is some kind of motor which is connected to some kind of pulley, and then we have these counterweights, and then we have this carriage in which people get in and get off. So every time a bunch of people get in, there's going to be an increase in the load that's being experienced by this pulley, right? And we'll define what torque is later, but every time a bunch of people get in, the torque increases. When the people get off the elevator, the torque reduces. So what we want to be able to do in the lab is we only have this motor in our lab, and we want to be able to create scenarios on this motor shaft, same as what would happen in real world, where the torque changes suddenly, increases, comes down, goes up, comes down. 5 people can get in, 2 people can get in. The speed should remain the same irrespective of how many people are on the elevator, otherwise it will become an unpleasant ride. So in the lab, what we'll do is using this generator, we are going to create these different torque profiles on the motor. Okay? So this motor is going to rotate at some speed. So if you look at this plot of this motor speed, omega, you're going to have some speed. And then using this generator, what I'm going to do is I'm going to suddenly put a load torque, suddenly reduce the load torque. But what I want to observe is the speed should remain somewhat constant without varying too much so that the right.
But we always use the DC generator.
What was it?
Why do we always use the DC
Oh,
generator?
you use DC generator because it's just easy to operate, right? You can replace the DC generator with a permanent magnet motor and operate that as a generator too. Just that the control for permanent magnet motor is a little bit more complicated, not suitable for undergraduate level, so we stick with a DC generator. Right? You could use anything. You could use induction, you could use a permanent magnet, you can put anything on the other side, right? And you can make it operate as a generator. Okay, any other questions? All right, so this is what we are trying to achieve. We have the motor, we are going to put some voltage on it, see what the speed is, and then using the generator, we are going to put like different load torque profiles and see what happens to the speed of the motor. And towards the middle of the semester, we will end up designing a controller so that irrespective of what load torque we throw on this motor, the motor speed remains a constant. So that will be our objective. But for today, we are just going to look at what is going to happen as I ramp up this voltage, what is going to happen to the speed. And without any control algorithm, once I start applying different load torque, what is going to happen to the speed? That's all we're going to see for today. Right? Anybody got any questions on the setup that we have?
Can you just remind me what PMAC stands for?
Power electronics. So power electronic converter. So give just a cursory idea of what's going on inside. So the DC voltage is coming from here, and then these are just a bunch of switches, and these are the leads that are coming out of it. So we have a motor in between here, right? So if I turn this switch and this switch on, I'm connecting the motor directly to 40 volts. If I turn instead this switch and this switch on, and while keep these two off, right, I reverse the polarity of the voltage that I apply, and I'm putting negative 40 volts on the motor. And if I do this fast enough, I could create voltages somewhat in between. So if I turn the switch on half the time, turn the switch off half the time, I would end up creating an average voltage of 20 volts. All right, and then I pass it through some filter, which essentially is not needed for this kind of setup, but let's assume we pass it through some filter so that it gets a nice smooth value, and that's what we end up seeing, right? So that is the basic description of what's going on there, but it's a little bit more complicated, but we will look at that in week 2. Okay, so let's start off with our DC motor. So the model that I have here, This top part, that is what is controlling the voltage for the motor. So when I slide this voltage, it is basically telling the two legs that I drew here, right? So these two, if I give a PWM of 100%, then the top switch will always be on. If I give a PWM of 0%, the bottom switch is always going to be on. Right? So that's all this block is doing. So the first one is controlling the left leg that I've drawn, the two switches, and the second one is controlling the right leg that I've drawn. And I can set any kind of voltage here, and the output voltage will be generated by the black box that I have here. Right? And then the second one that I have here, so I can add, so same thing happens in this section. I add some voltage and the voltage comes out of it. But I actually want to do some kind of control in the second one because I want to create some kind of torque profile. So what the second one is doing is measuring the current, and from the current it can estimate what the torque is being. And then if the torque is different from the value that I asked it to create, it will generate some control algorithm and then change the voltage so that the torque that I ask is the torque that's being outputted, right? We will figure out every single aspect of this, how to design the controller, everything later. But now take it for granted that if I ask for a particular torque, it is going to give me that exact torque value, right? So what I'm going to do is start increasing the voltage of the motor. And then once the motor has reached its maximum speed, full voltage, I'm going to start increasing the torque. What I want you all to guess is what is first going to happen when I keep this at 0 and start increasing the voltage. What is going to happen to the motor speed? Just take a guess. It's a DC motor.
Increase.
It's going to increase. All right. Any other answers? Everybody thinks it's going to increase. Once I start increasing the torque, any guesses?
Decrease.
Decrease. So we all have an intuitive feel for what is going to happen. Let's just verify if it's correct. So let me start increasing the voltage. I need to program it first. Speed is initially 0. Let me increase the voltage. Those of you in the front row can probably confirm if it's rotating or not. Right? So every time I increase the speed by a step, the voltage by a step, the speed is going to increase by a step as well. Right? So every step I create, it's going to increase it. So let me go all the way. And those of you in the front row can confirm that I'm not lying. The motor is actually rotating. All right. So when I increase the voltage, the speed increased as you all predicted. Right? And now I'm going to start applying the load torque. So, right. So here we had 0 load torque. We increased the voltage. The speed started to increase. And next, I'm going to keep the voltage constant at its maximum value that can be generated by the converter for a given 40 volts DC bus. Right? So we are going to retain the voltage constant. And we are going to look at what happens to the speed as we start increasing the load torque. Right? And it starts to reduce. Right? So let's look at that. Right. So let me increase the torque. Those of you in the front row can already hear the sound change. And in the plot, we can see that the speed came down just a little bit. And let me just do the full step. The speed just goes down in multiple steps, right? And now if I reduce the load torque back again, the speed will come back up again. As simple as it. So if the load torque increases, the speed has to reduce. If the load torque goes back down, the speed will start to increase. Anybody want to give me a reason as to why this is happening? Why the load torque get better?
Which part, at the beginning or the end, or?
I'm not worried about the beginning. I'm worried about the second part. Beginning, we need to cover a little bit more theory to be able to get to it. Why the torque?
You're drawing more current, so it's taking energy from. It has to decrease.
I see. Right?
It's creating a back EMF that takes away from the voltage being applied to the motor.
Right. But once we get to a particular speed, the back EMF is a constant. Right. So that you're right. So what Ben mentioned is it's a very good guess, though, Isaiah. But so this would have given you a little bit of insight as to what's going on. But I said we are basically measuring current and converting it into torque. If I need higher torque, that means the current is also increasing. When the current increases, since this is a whole bunch of copper coil, when current increases, the drop in the resistor of the coil also increases. Right? The voltage dropped in a coil resistor is going to be IR. So whenever the torque increases, the current has to increase in the motor. And we should have seen, we have already seen the formula, right? Force was Bill, L times I cross B, or I times L cross B, whichever convention you like. So if I need to increase the torque, which is related to force, which we'll derive, then the current should have had to increase. In this motor, it's a permanent magnet. The B field is not changing. It's only the current that's changing from the power converter. So the current increased, the force increased. And if the current increased, this current flows through some coil, right, which has some resistance, some inductance. And when it flows through the resistance, it's going to drop some voltage. So the available voltage is reduced. Right? And we already saw when the voltage is lesser, what would happen? The speed will have to come down. All right, so that's what's happening there.
Does that mean if it's at a higher voltage, it can like handle a bigger change in torque more easily?
Yep. So if you were at higher voltage, you wouldn't see that much drop. Any other questions? Okay. So this is what the DC motor behaves like. Let's look at what the AC motor is going to behave like. Let's start off with the simple one induction motor. So the induction motor, unlike the DC motor that we just saw, is an AC motor, and we just cannot apply a DC voltage to the motor and expect it to rotate. So we have a different control mechanism when it comes to both induction motor and a permanent magnet synchronous motor. So we use this control mechanism called V by F control, which basically states that, let's say we are applying some voltage, and we are just going to look at one phase of the voltage. There are other two phases in the motor, which would be 120-degree phase shifted from this. We'll look at all of those a little bit later, but for now, just look at the voltage of one particular phase alone. And let's say this is at 60 Hertz. So the time period for one full oscillation is about is 1 by 60. And this is a very low voltage motor that we have on the table because we want it to be extremely safe for the labs. So that's the reason why you're allowed to do these labs alone without any TA supervision or any instructor supervision, because nothing you can do can either hurt you or damage the equipment in any way. More importantly, it doesn't hurt you. So it's rated for very low voltage. So at about 60 Hertz, the rated voltage of this motor is about 22 volts peak voltage. And what this V by F says is that voltage by frequency ratio must always be kept a constant. So what that means is if I now want to run this motor at 30 Hertz instead of 60 Hertz, right, that basically means I want to run the motor slower as well. The voltage would now have to be 11 volts, such that the V by F ratio is always the same. So this is 1 by 30 Hertz. So previously we had 22 by 60, which is going to be same as 11 by 30, right? This is not always strictly followed. For instance, when you go to very large frequency, that would also mean that you need very large voltage, but we have a limited DC bus voltage. So there comes a point where the DC bus can't generate any more voltage and the motor will go into a mode called flux weakening. But we'll ignore that extreme scenario. And we'll also ignore the lower the speed range, where at very low speeds, initially, particularly while starting, there is a lot of static friction. And to overcome that static friction, you still need some amount of sufficiently large enough voltage that after dropping across the resistances, there is enough current to create flux, to create force, to be able to rotate the motor. Right? So at the lower part also, we won't follow the V by F ratio. At higher region also, we won't follow V by ratio. In between, we'll follow the V by F ratio. So if the frequency increases, the voltage will proportionally increase in this particular range. After a certain range, over the limit, DC can't generate the voltage. Lower limit, we want some voltage to get the motor spinning in the first place. All right, so we'll look at only this region. So in the induction motor, you can guess what the speed of the motor would be, very close to the value of what it will be under no load using this formula. It's a very simple derivation which we'll do later. But what it says is given the frequency and the number of poles in the motor, the number of poles in the motor that we have on the table is a 4-pole motor. Typically induction motors, if you were asked to take a guess, induction motors typically would either be a 4-pole induction motor or a 6-pole induction motor. It's very hard to find 2-pole or 8-pole induction motor. Okay, so for commercial applications at least. So we are running it at, let's say, 60 hertz and we have 4 poles. So that comes to about 1800 RPM. Right? And if you run it at 30 hertz, it will be very close to 900 RPM. So this is under zero load torque, when there is no load torque applied onto the motors that we have. So this would be the waveform that we get. This will be the speed at which it will rotate, right? So let's go back to our model. So I'm not going to increase the voltage. I'm already going to run it at rated voltage at rated frequency. So that is what this block is doing on the top here, right? It's already decided to run it at whatever rated voltage is at a rated frequency, which is 60 hertz for this particular motor. Actually, we'll design in India, so it's 60 hertz for this particular motor. Change the connection, just a second. One is done. That's much better. Okay, so the speed is going whatever it is going at. So the scale here is radians per second, not in RPM. So once I start increasing the load torque, the speed starts to drop. And as I keep on increasing it, the speed will start to gradually drop further and further, right? The reason for this drop is not as straightforward as the case we had with DC motor, where it was just a pure resistive drop. But something interesting will happen as I keep on increasing this torque further and further. So let me put this in correct focus, okay? So when I increase the torque too much, someone in the front can confirm if the motor actually comes to a full stop. Does it stop? Mm-hmm. All right. So if you go look at the speed, so if I increase the torque too much, so when my torque is 0, the speed was at its maximum value, very close to 1800 RPM. And as I start increasing the torque, the speed starts to gradually drop. And if I exceed the maximum amount of torque that can be generated by this motor, the motor would come to an abrupt stop. And if I were to reduce the torque again, the motor would go back to operating at the speed at which it could support the torque that is being requested by the load. Right, so this is the biggest advantage when it comes to an induction motor compared to a permanent magnet synchronous motor, as we'll see in a minute. In an induction motor, there are two things. First, if you exceed the load torque and the motor comes to a stop, you can always reduce the load torque down again. It will come back to operating at the same speed that it was operating before it came to a halt. And the other biggest advantage is, as you saw, I directly started at the rated voltage and the rated frequency. I didn't increase the voltage to that value slowly. Right? That means what it effectively means in reality is you can take a 3-phase induction motor that's rated for say 220 volts, then you can directly connect it to a 220 volts 3-phase system outlet directly to the wall without having to gradually ramp up the speed of the motor or any such thing. Right? So it is extremely robust in that sense, and that is what has made it the workhorse of industry. So let's go back to the model. So now the speed is 0. Let me start reducing the torque. Still plotting. Right? Can somebody confirm it started rotating again?
Yeah.
All right, fantastic. So if I were to reduce the speed and it comes to if I put too much torque on the motor and the motor comes to a stop, you can always reduce the torque and the motor will start back up again. This is the reason, this is the major advantage of an induction motor that the first thing is, if you look at the voltage that I applied here, I directly applied the rated voltage at the rated frequency. So that's the first advantage of an induction motor. You can directly take an induction motor and connect to the wall outlet, a three-phase wall outlet, and the motor will start rotating. All right, and it'll go to the speed that it has to go to for the particular frequency. And then in the industry, if you start applying more and more and more load torque, and the motor comes to a full stop, it's not going to damage the motor. You reduce the torque again, and the motor will start back up again as if nothing had happened. All right. Now let's look at the case of a permanent magnet synchronous motor, which performs somewhat fascinatingly different from both of these motors. This one doesn't trouble me as much. It's closer. So in case of permanent magnet synchronous motor, I have to do something a little bit different. The first thing I need to do is, in case this has a magnet inside, and I don't know where the magnet position is. All right, the encoder doesn't give me where the magnet position is. The encoder only tells me how much the rotation has changed. It doesn't tell me absolute where the magnet position is. So that's the kind of encoder that we have. So what we have to initially do is excite one of the phases so that the magnet aligns with that particular phase. Then we know where the initial position of the magnet is, and then we can start continuing rotating. So the first one that I'm going to run is basically a model called rotor in it. It does nothing, just initially rotates the magnet to one particular position that I like. The person in the front might be able to see a slight jolt when I do that. And afterwards, we'll go back to running this V by F model. Same thing as for the induction motor, that model that I had drawn before. Okay, so that should be done. Change V by F. Now let's run this. So in case of permanent magnet motor and an induction motor, I directly started with the rated voltage, rated frequency. That cannot happen in a permanent magnet synchronous motor. I need to gradually ramp up the voltage. And every time I ramp up the voltage, the frequency is also proportionally ramped up. So what I want you to first guess is, if I start increasing the frequency, what is going to happen to the speed of the motor? Go up proportionally or? All right. So when I start increasing the frequency using the V by F rule that I mentioned earlier for a permanent magnet synchronous motor, as I increase the frequency, the speed increases linearly. Not approximately linearly, it's perfectly linearly, right? So let's see if that is the case. It's rotating. Is it rotating? And if you look at the speed, if the speed does go up proportionally for every step I take in the frequency, the speed proportionally goes up. Right? We have reached full speed. Now, can everybody guess what's going to happen if I start increasing the load torque? In case of an induction motor, the torque started to, the speed started to reduce if I increase the load torque. In case of a synchronous motor,
Do the same.
say the same. Why?
Synchronous.
Right, perfect. That was the answer. The theory is complicated, but it's called a synchronous motor because irrespective of what load torque you apply, the speed is always going to remain the same. All right, that's the reason why it's called a synchronous motor. So let's look at that. Let's start increasing the load torque. Will it always remain a constant? No. So at some point, if we apply too much load torque, it would come to a complete stop. Can you let me know when it stops? Still not? Stop. Okay. Okay. So It has come to a stop, right? So it was synchronous all the way and then it suddenly stopped when the load torque increased. What do you think is going to happen if I start reducing the load torque now? Is it going to come back up online again? No. So let me reduce the load torque. I can take it all the way back to 0 and you can confirm that it's not rotating.
Google.
All right. So I can take it all the way down to 0 and it's still not going to start rotating. Right? So if you look at the plot, it's not going to rotate. So this is a very big problem when it comes to permanent magnet synchronous motor, because if we were to directly connect this motor to the grid, let's assume that's somehow feasible, as we'll see in a minute, that is not. And for whatever reason, we apply a load torque that's large enough that the rotor comes to a stop. There is no way to bring that motor back up online again. Right? As we saw, you can reduce the torque all the way down to 0 and the motor is not going to start rotating again. So this is the first problem. And the second problem is when the rotor is spinning, there is something called a back EMF that's induced on the stator winding, which then limits the amount of current that flows into the stator winding. This is extremely critical. When the rotor comes to a stop, the back EMF goes to 0. So from the grid's viewpoint, what it looks like is basically a pure resistor with some inductance, which typically, let's assume, is very low for a permanent magnet synchronous motor. So it's some resistance connected across, very tiny resistance connected across a very large voltage. For a large motor, let's say about 5 to 10 horsepower, stator resistance of about 10 milliohms is not very unreasonably low. So if you connect it to 220 volts with a 10 milliohm resistor, you can think of how much of current is going to flow in the winding. It is going to be far higher, orders of magnitude higher than what the motor is rated for. So there will do two things. First, it will burn the winding, stator winding. And when this happens, if your rotor is aligned in such a way, rotor magnets are aligned in such a way that the flux produced by the rotor magnet is opposite the flux produced by the currents flowing in the stator winding, the flux due to the stator current flowing in the stator winding can end up demagnetizing the rotor magnets. So this is a very huge problem that could not be addressed properly without use of power electronics. So in the past, permanent magnet synchronous motors did exist, but they used to have a whole bunch of resistor networks connected in series to handle all these inrush current, to bring it slowly into synchronization and so on and so forth. It was a big hassle. Compare that to induction motor, you can directly connect it to the grid and it will start spinning without any problems, right? So that was the reason that permanent magnet motors typically stayed within the auspices of generators alone. On the grid side, generation is always permanent magnet generators. But when it came to load, particularly industrial loads, it ended up being induction motor became the most prominent motor because it's extremely robust, right? So, but with the advent of power electronics, there is no longer that limitation. Power electronics have become cheap enough that permanent magnet motor with the power electronic converter connected to it can compete with the induction motor. And gradually, many induction motors are getting phased out with permanent magnet motor connected to drive, particularly because it's more efficient, right? It can it consumes far lesser power consumed to an induction motor. Also, the quality of the power that's being consumed by permanent magnet motor is far better. It's very close to unity power factor if the control is done properly. Right, so these advantages make it very lucrative for as we go forward with more energy efficiency conscious mindset. The reason power electronic converters help is because if the rotor comes to a stop, the converter can detect it and then stop applying the voltage, right? And if it comes to a stop, if the load torque becomes low enough that the motor can spin up again, it can start applying very low voltage at very low frequency and then gradually ramp it up all over again. When you connect it directly to the grid, you don't have that option. It's always the given voltage at the given frequency. All right. So with that, we are done with the introduction. So for the rest of this next 3 weeks, we are going to be looking at 3 fundamental concepts. So we are going to look at for this next week, we are going to be looking at basically this tiny coupling that goes on between the motor and the load, or basically the mathematics of this structure that we have here. And it's given by a very simple equation, extremely elegant equation. And you'll see the similarities between the electrical system and the mechanical system quite soon. So this is the equation that we are going to try and derive for next week. All right, so we are going to model the mechanical system of this whole power supply and the inverter and the motor all connected together. We are going to figure out what this equation represents and how do we get here. And then the week after that, a week and a two, we will spend on looking at how this torque is generated in the first place. Right, how a current carrying conductor interacts with the magnetic field to create a force, and then how it becomes into torque and so on and so forth. So we'll dive into great detail about Maxwell's equation. We'll look at all the four equations and the Lorentz force equation, and we'll try to get into the weeds and the details and derive every single one of the equations that we have seen in our basic circuits course or other electromagnetic theory course. Right, so that's what we'll be doing after that. And once we are done with that, we are going to be looking at how this power electronics, right now we are just calling it a black box, but we are going to see how this power electronic converters operate, in particular how a H bridge operates to generate this voltage that we want at the output of the converter. So once we have covered all of those three critical tools that we need, we will then go and apply those things that we learn into figuring out how a DC motor works, how a AC motor works, and then we look at how to control this DC motor. We'll create speed controller, basically think of an application like you're going in a car and you said it, you want it to go at some particular speed, right? And the car should go at 60 miles per hour, irrespective of whether it's uphill or downhill, irrespective of what the load torque conditions are. Right? We want to go at the same speed, or same in the case of an elevator. Irrespective of whether there are 5 people in the elevator or 10 people in the elevator, you want the ride to be consistent at the same speed. So how do we design a speed controller? Because we saw that DC motor, induction motor, they don't have the same characteristic, right? They all have the speed drop if the load torque increases. So how do we circumvent this characteristic? By putting a controller on it, which can overcome these limitations that are found within the motor themselves. So we'll look at how to design these controllers, and we'll also see how to do torque control, typically used in like traction application, or how to do position control, like the camera that we have right there. I ask it to go to a particular angle. It's basically having a controller with a DC motor or a permanent, be it brushless DC motor, which basically does some kind of control and goes to whatever angle I want it to go, or a robotic arm in an assembly plant and so on and so forth. So we look at all of those later, but we need these three fundamental tools to build on top of it, right? So in this class, we are going to be deriving every single equation, except if it is a fundamental law of nature for which there is no deeper underlying equation, or if we are going to call it a definition. All right, and when we define something, we have to be extremely careful. When we define some variable here, we cannot redefine it sometime later. And I've seen this done quite often in almost all courses, where we define something, for instance, power, we are going to be defining it as force times velocity. And if you go to a circuit analysis course, the first thing in a couple of lectures later, you would redefine power as voltage times current. That is completely a no-no in this course. If we define power as force times velocity, we are going to stick with it. And then we are going to prove that voltage times current is same as force times velocity. All right? If we can't do that, we cannot redefine it ever again. So in this course, we are going to be very particular about every single term that we use. We are not going to take any equation for granted, any symbols for granted. All right, with that, let me start off with a few simple definitions that we all would have learned in our 6th or 7th grade when we learned about Newton's equations, Newton's law of motion. All right, so let's see. The first one is define velocity as the rate of change of distance, displacement. And we're going to define acceleration as the rate of change of velocity. Right? And then we're going to define momentum as mass times velocity. And we're going to define force as the rate of change of momentum, which in turn is equal to anybody?
Mass times acceleration.
Right, mass times acceleration. Is that always true? When does it fail?
Mass is constant.
When mass is constant. In case of rockets, when mass changes, this cannot be used, right? The M has to be constant for us to do that. In our case, we are going to assume that M is always constant. As the motor rotates, we do not expect the mass to change, because if the mass were to change, something has horribly gone wrong, right? So we do not want that to happen, and we're not going to look at such scenarios either. And then the final two equations that we are going to define is the work done. I interchangeably use the symbol E for energy or W for work, both are one and the same. When we are talking also about electric field, I'll use W, and there is no mention of electric field, I'll go back to symbol E. So this is integral f dot dx, right? And then the final definition is our power, which is the rate of change of energy, rate at which work is done. So if you do the differential, plug in the above equation, it's force times velocity, right? So basic definition. Again, here I'm calling them definition, but these are all over centuries of work done to look at what is happening physically and come up with a relationship that would explain what is happening physically. Force is something that we feel. Momentum is something that we feel, right? It's not just a pure definition alone, but empirical observations based on looking at the potential and kinetic energy and so on and so forth. People have come up with these set of fundamentals equations, basically encapsulated them all in the Newton's laws of motion, right? So these set of equations, we are going to call them definition and take them for granted going forward. All right, so I have another 2 more minutes. So let me ask you a quick question. Let's say I am putting a lot of effort, exerting a lot of effort and pushing hard on this board. Am I doing any work or am I not doing any work? Again, there are no wrong answers in this course. This question seems to confuse a lot of people, because depending on who you ask, the answer seems to change. Anybody want to take a guess? No work is done? Why am I feeling tired then?
You didn't do your push-ups this morning?
What was it?
You didn't do your push-ups this
Do I
morning?
look like I do push-ups every morning? Of course, from the formula, sorry to change the camera angle. So if I keep pushing on the board, the answer is I'm not doing any work. And we can see from the formula that the work is integral f dot dx. If displacement is 0, then there is no work done. If you ask a physicist, they would say you're not doing any work because there is no displacement. If there is displacement, the board would bend and we will be able to see it. But if you ask a biologist, they would say, of course, you're doing a whole lot of work because your muscles are contracting and you're expanding energy. But if you ask an engineer, they would say, I don't know. So in reality, when I push on this board, I am spending energy, I am doing work, but the board is not gaining any energy. All right. So there is a difference between doing work and spending energy versus transferring energy to another medium. So let's see what's going on in our own muscles. So it is an extremely fascinating way how it works. It's a biological motor, right? It's a biological linear actuator, biological actuator. And millions and millions and millions of years of evolution has led to this machine that can do extremely efficient work that we yet still cannot replicate in spite of all our knowledge. So let's see how it works. So our muscles basically composes of two long proteins, myosin with segmentations every now and then, and actin. So these are long protein fibers, right? And these myosins have this head, the myosin head, right? To which there is a adenosine diphosphate ADP molecule and an inorganic phosphate attached to this in this particular state. This is the energized state for the myosin head. right? But the state the myosin head would rather prefer to be in is this de-energized state, where it's kind of bent, but as soon as it goes to the state, by whatever mechanism, we'll take a look, ATP molecules, which is adenosine triphosphate, this has an extra phosphate group attached to the end of the chain. This immediately goes and binds on to this unexcited myosin head. And as soon as it attaches, it splits into ADP and an inorganic phosphate. And in the process, when ATP, due to hydrolysis, breaks down into ADP and an inorganic phosphate and releases energy. So this is the energy storing mechanism in all living organism. The discovery of this, I think, got the Nobel Prize in 1925 or some, a later part of 1920, right? So, yeah, so in all our energy organisms, when you eat food, basically the glucose gets broken down due by oxidation and breaks down into about 40 ATP molecules, which are basically energy stored. And then whenever the energy is needed, hydrolysis breaks down ATP to ADP and takes some energy out of it. So as soon as this, excuse me. So as soon as this ATP binds and breaks down into ADP and inorganic phosphate, that energy that's released pulls this myosin head backwards. So you can think of it like a spring. Spring would like to be in a compressed state, but you're putting energy and pulling it apart. So that's exactly what this ATP does. When it breaks down, it transfers energy and pulls this myosin head to an energized state. Now what happens in a spring, when you leave the spring, it brings down all that energy back out again. So if you attach a block of mass, at the end of it, it's going to pull the mass inwards, right? So this energy is all packed in and it's ready. If it goes and attaches to something and that energy is transferred to that, it's going to pull it back exactly like how a spring would be doing. So what happens on the actin side? So what happens on the actin, if you look at how the actin looks like, actin has these. Actin is basically made of these long chain molecules, whole bunch of them, going all the way, spiraling, coming back, and so on and so forth. Right? Every single place. And each of these molecules have this site called myosin binding site. Each of these has this site where this myosin head would want to go and bind right away. They have an affinity to go and stick to those points. But what is preventing them from going and sticking to those points is a long chain molecule called tropomyosin. So that goes, extends and comes and covers all of these active binding sites are being covered by this tropomyosin. All right, and then these tropomyosin, every now and then on its chain, there is another molecule called troponin. That keeps repeating every now and then, right? So the moment your brain cell sends a signal to your muscle saying that, hey, you need to contract, for whatever reason, you just need to contract. So what happens is the nerve cells send a signal, and then the sarcoplasmic reticulum receives that signal. They release a whole bunch of certain pumps, the sodium channel pumps get activated. It's a very complicated process, which then ends up releasing a whole bunch of calcium ions into this channel that we have here. So there's a whole bunch of freely floating calcium ions everywhere. And this calcium ion has an affinity to go and bind to troponin. And what interestingly happens is, as soon as this calcium ion goes and binds to this troponin, so this goes and binds to this troponin undergoes a shape transformation. So basically, what is a flat structure now gets a bend in its structure. And what happens is, as it bends, it moves this tropomyosin to which it attached as well out of the way, and thereby exposing all these myosin binding sites which were previously hidden by the tropomyosin. So that calcium binding is very important because that's what causes the shape change. And there's a very common phenomenon that happens, the shape change in molecules during a whole bunch of DNA transcription and all of those. You can see this mechanism come again and again in different forms. So once these the myosin binding head sites binding sites are opened out, the myosin has a very high affinity to go and bind. And what it will do, it will go and bind to those active sites that just opened up because of these fiber moving out of the way. So this goes and attached to this, right? These molecules are very close by one another. So this goes and attached to it. And as soon as this attachment happens, this inorganic phosphate that was previously attached to it gets dropped by the myosin head. So this is lost and it moves away. And once this inorganic phosphate is moved, this myosin head is no longer being prevented to go back to its original state, right? Which is this de-energized state. This phosphate that's attached was keeping it in this particular shape. But the minute it drop out, it would want to go back to its original state, which is basically this bent kind of shape. So as soon as this attachment happens, it goes back to its bent shape by dropping off the inorganic phosphate. And when it goes back, since this is now solidly attached to this, it is going to pull the actin strand backwards as well along with it, right? And what happens? You get a muscle contraction. So this is how basically muscle contractions happen. And after that, what happens at the very end of this knock, where the myosin head has gone back to its completely original state, these ADP molecules also drop out. And we already know the cycle again. Once the ADP molecule is dropped out, this is now primed up for ATP to come and attach, because ATP now has an affinity to go and attach to this unexcited myosin head. So now ATP attaches, it breaks down into ADP and inorganic phosphate, and the whole process happens again and again and again, contracting it further and further and further. All right, so this is how muscle contraction happens. You have contraction where the length changes. So when I say pull my leg up, right? So the length is changing in my muscle. So the length of the muscle changes. In those cases, this is basically progressively pulling it backward and backward and backward. In isometric muscle contraction, where you're just kind of say pushing on the board forever, right, without doing any kind of length contraction, it falls under the category of isometric muscle contraction. So you might ask the question, it was already attached, the muscle came back, it contracted, why is energy being continuously spent if I keep on pressing on this board, right? The answer is because every time this attaches, after some time it will drop out and disconnect, right? And this is going to go back to its initial state. So million other myosin heads keep doing the same activity where they attach, pull it back, drop off, attach, pull it back, drop off, and this keeps on going back and forth and back and forth. So even though this attaches and pulls it back, it has an affinity to go back to its original state, relaxed state, and something needs to come back and pull it back up again. And a single head cannot be attached to a myosin head for too long because it will undergo a process called fatigue. Similar to when you have a spring that's stretched out for too long, it is going to lose out its elasticity. Same thing will happen with the myosin head. So evolutionarily what happens, it basically breaks back and goes back to its default state. And then needs to be energized, pulled back again, goes back to original state, pulled back again. So even though you're just pushing on the board, there is no effective length contraction. Your muscle does remain contracted, and you always keep on spending this ATP molecule, which is basically energy. And in the process, basically you spend energy in the friction in the muscles going back and forth, and your body starts to heat up. You know, if I keep on pushing this for too long, I start to heat up, my muscles start to get weak, I start to sweat, and at some point I get too tired, and I want to end this lecture as soon as possible. All right. So with that, we are done with today's class. We will continue on next Wednesday. There is no homework this week, but next week on we'll have homework. So enjoy this weekend as much as you can.